Hello everyone, I am Faghih from the University of Tehran, and today I want to present my work with my student Hadi Moloodi and Professor Borzoo Bonakdarpour from Michigan State University. The title of our work is Parameterized Distributed Synthesis of Fault Tolerance using Counter Abstraction. Let's start by motivation. Distributed algorithms can be subject to different types of faults. Therefore, providing fault tolerance for these algorithms is very important. Designing fault-tolerant algorithms is a challenging task, and proving their correctness can be even more difficult. So, an active research area is to automatically synthesize fault-tolerant algorithms where the resulting algorithm is guaranteed to be fault-tolerant. Looking at the literature, there are techniques for synthesizing fault-tolerant algorithms from their specifications. There are also techniques for repairing fault-intolerant algorithms by adding fault tolerance to them. The limitation of these approaches is that they are topology specific, meaning that the synthesis algorithm works for a distributed algorithm with specific sizes. In other words, the resulting algorithm is fault tolerant for example, a system of size 5, but may not be fault tolerant for a system of size 6. And the runtime of these algorithms grows exponentially by the number of processes. So the idea is to propose a parameterized synthesis where fault tolerance is added to a process template, and the goal is that any protocol instantiated from the resulting template that is instantiated for any number of processes is fault tolerant. So let's have a brief discussion of the preliminary concepts. A process template is a tuple of V and G. V is the set of control variables, and each process has a set of variables. Each variable is either local, meaning that it can only be read by the corresponding process, or shared, or a variable can be shared, meaning that it can be read by all processes. G is a set of guarded commands that identifies the actions of processes. There are a number of fixed processes that are instantiated in every protocol instantiated from the process template, and Ka identifies the number of these fixed processes. Other processes are called parameterized processes. As an example, consider the Byzantine Agreement Protocol, where the goal is that processes make an agreement on one value. There is one fixed process in this protocol, which is the general process, and the parameterized processes are the lieutenant processes. In terms of variables, each process has a decision variable which can be undecided or bottom, 0 or 1. This variable is shared, meaning that every other process can see this variable. There are two local variables for each process: finalization bit, which shows whether or not the decision of the process is finalized, and the Byzantine bit that identifies whether the process has gotten faulty or not. This is the process template for our Byzantine agreement example. You can see that the variables are identified along with their initial values, and you can see the guarded commands. The first one corresponds to the fixed process, which is the general process. It changes its decision from bottom to 0 or 1 and sets its finalization bit to 1. Each parameterized process or lieutenant copies the general's decision and then finalizes its decision. And this is the fault-intolerant version of the protocol. Now, let's quickly review the concept of fault tolerance. We have two types of specifications: phi complete, which should be satisfied in the absence of faults, and phi safety, which should be always satisfied whether or not fault has occurred. For example, For the Byzantine agreement example, it includes these properties: validity, which means if the general process is non-Byzantine, then the final decision of no non-Byzantine lieutenant process can be different from the decision of the general process. Agreement, which means no two non-Byzantine lieutenant processes can finalize to different decisions, and termination, which means a finalized decision cannot be overturned. This is Byzantine agreement protocol with fault. As you can see, we specify the faults using guarded commands. The first guarded command shows that we assume there exists at most one faulty process. In the second guarded command, we identify that the faulty process can change its decision and finalization bit arbitrarily. To formulate the fault tolerance problem, we need to define the set of legitimate states, which are the states that the protocol resides in unless a fault happens. So these are the properties of LS. LS is closed. Any computation starting from LS satisfies phi complete, and those computations need to be infinite. Now, a protocol is fault tolerant if and only if it satisfies this property, which means it always satisfies phi safety, and if it goes outside LS because of a fault occurrence, it eventually goes back to LS. Now let's see how we add fault tolerance to a process template such that every instantiated protocol from it is guaranteed to be fault tolerant. To deal with a parameterized problem, we need to use some kind of abstraction so that we can handle the infinite number of protocols. In this research, we have used an abstraction called counter abstraction. In 0, 1, 2, up to L infinity abstraction, we know the number of parameterized processes in each local state, whether it is none or 0, exactly 1, exactly 2, up to exactly L, or it is L plus 1, which means the number of processes in that local state is more than L. As an example, consider a 0, 1 infinity counter abstraction for our Byzantine agreement example. Each process has 12 possible local states based on the valuations of its variables. So each state in counter abstraction is represented by 12 tuple, where the number of each element corresponds to the abstract number of processes at one local state. For example, here we see a transition from one abstract state to another abstract state. If the first element corresponds to the local state with decision bottom, finalization bit of 0 and Byzantine bit of 0, and the 8th element corresponds to this local state that you see, this transition corresponds to one process in the local state in the first element, changing its decision to 1. There is a concept called read-write restriction in distributed algorithms. It means the action of each process does not depend on the variables it cannot read. So if two states are the same except for the values of the variables not in the read set of a process, and the process has a transition starting from one of these states, it has similar transitions starting from the other one as well. For example, in a Byzantine agreement protocol with 3 processes, these 2 transitions have the same effect as far as process 2 is concerned. Since process 2 cannot read the finalization bit of process 3, which is the difference of these 2 transitions. This implies that if transition 1 is included in the set of transitions of a distributed program, then so should T2. We have extended this concept to the counter abstraction to respect read-write restriction in our synthesis algorithm when transitions are added or removed. I skip the details to respect the time limit and invite the interested audience to read the paper. Now let's take a look at our synthesis algorithm. It consists of 7 steps that are repeated until a fixed point is reached. In the first step, the abstract model is generated from the fault intolerant parameterized system based on counter abstraction. In the second step, We label each transition with two indexes showing which local states get incremented and decremented by that transition. And it is done based on the logic of the original algorithm. For example, consider this transition in our Byzantine agreement example. We can see that the number of processes in the local state at the second element is decremented, but it is not obvious which local state gets incremented, the first one or the eighth one. And so we can label the correct local state based on the logic of the algorithm in this step. In the third step, the unreachable states of the model are removed. An unreachable state is one with no incoming transitions. In the fourth step, bad states are removed. A bad state is one that violates the safety specification. To remove a bad state, we make it unreachable. If a bad state is reachable from a set of states only by faults, they also become unreachable since we do not have control over the execution of faults. In the fifth step of the algorithm, we deal with deadlock states. Deadlock states are not allowed. They are not allowed in LS because of our problem statement, which says LS should have infinite computations, and it is not allowed in non-LS since it would violate fault tolerance and recovery to LS. To remove deadlock states, we add recovery transitions to them. We have specified the conditions for adding recovery transitions. The first condition is asynchronous condition, meaning that exactly one process should execute it in a transition. The second condition is that the recovery transition should not violate the specification. The last condition is that by adding a transition, we should not create cycles in non-LS. Cycles would violate the recovery condition of fault tolerance. In abstraction, like in counter abstraction, that model that we have, not every cycle can be instantiated to a cycle in a distributed protocol. So we call a cycle bad cycle if there exists a system instance for which the bad cycle is instantiated to a cycle. In the paper, we have identified two categories of spurious cycles and discussed how we recognize them. And I have to skip them in the presentation because of the time limit. In the sixth step, deadlock states that could not be resolved by adding the recovery transitions are made unreachable. If the state is reachable by fault, we backtrack and make the source of the fault unreachable as well, since we do not have control over faults. Considering the conditions specified in our problem statement, we have proved the soundness of our synthesis algorithm, meaning that if the synthesis is successful, the resulting template is guaranteed to be fault tolerant. We have fully implemented our proposed algorithm and have done experiments on 4 well-known distributed problems. This table summarizes our experimental results. Here you can see the faults we have considered, the synthesis time, and the abstraction level. We tried synthesis starting from abstraction level 1. If the synthesis algorithm fails, we increased the abstraction level and repeated the synthesis algorithm. To conclude, we have proposed an automated technique for parameterized synthesis of fault-tolerant distributed systems using counter-abstraction. We have fully implemented the algorithm and successfully synthesized fault-tolerant algorithms for 4 well-known problems in less than 16 seconds. Thank you very much.